Hello everyone, my name is Craig and I'm going to be your host for today's STK webinar. It's going to be on 11.6 and we're talking about what's new in EOIR. And we have with us today Pat North. He is our Chief Remote Sensing Engineer. And before I hand everything over to him, we encourage questions. So if you're falling behind or have a question on something that he just mentioned, please ask using the questions panel. In GoToWebinar, there is a questions panel, and if you type in your question on that screen, I'll see it on my screen, and I'll make sure to answer or ask those questions to Pat at the end of the webinar. So now I'm going to hand everything over to Pat so he can get started.
All right, great. Thanks very much, Craig.
There you go, Pat.
All right, hi, my name is Patrick North, and I'm going to talk to you today about what's new in 11.6 for EOIR specifically, and to cut to the chase, that's target signatures. And we're going to talk all about what those are, how you can use them, and sort of the integrated analysis that you can do now in 11.6 that you weren't able to do previously. So I've got Tall Bass here as well, and he's the one that helped me build a lot of these scenarios out.
Hey there.
So if you have any questions on these, we're actually going to demonstrate some of the scenarios that he built, and those are going to be online later. So you'll be able to actually check out the work that we've done if you wanted to base any of your own analysis off of one of these templates. So briefly, I'm going to go over the agenda that we're going to have today. I'm going to mention the tools that we'll be using. Then we're going to say, all right, well, what are these target signatures? And specifically, where can you use them? And I'm going to mention target signatures in general. I'm going to talk about, well, we've got ways to design these high-level sensor or target characteristics. That's great for doing laser modeling. And finally, what if you have a whole bunch of these illumination sources at once? Well, now all of a sudden you have a complex electromagnetic radiation environment that you need to worry about. So we're going to cover all three of these. Finally, we'll answer any questions and we'll wrap things up. So if that sounds good, we're going to try and also at the end of each of these sections say, it's great to use STK and EOIR for your analysis, but it's applicable at various different stages of your program, whether you're just starting out doing research and development or writing a white paper, or you're in the middle of a program and you're writing requirements and validating them and doing integration testing, or if you're operational and you're coming to the end of lifetime and you're trying to design new experiments and things like that. All of those are applicable for what we're going to be talking about today, if you're looking at specific targets that you know what they look like. So what is STK? The way I think about it is STK is a physics engine that gives you, your sandbox, which you can start playing with. And you can create things like ships, you can have aircraft, you can have satellites, ground stations, and you can have all of those moving in your real-time environment. But then on top of that, you can model many different domains. So for example, if you're an aviation guy or you're an astro guy, you can include aviator or astrogator. You can model specifically how those platforms of interest are moving. Or if you're worried about the space environment, if you're worried about space radiation, or if you're doing comms and radar analysis, or most importantly of all, if you're doing EOIR type of analysis. So if you've got sensors that are looking at the electromagnetic spectrum, that you're trying to add that extra layer of analysis capability. The output from all of this is both qualitative, so you've got nice pretty pictures, imagery, and quantitative. So you have real physics engines producing real numbers on the back end. And both of those are important because anytime you see a new type of phenomenology, you might deal with it day to day, but when you try and explain that to someone else who has to make a decision based off of that, it's nice to have that graphical aspect to explain why something is happening in an easy to understand way. And I'm going to make sure that we keep hitting on that. So EOIR, what is it briefly? It came from the Space Dynamics Lab, and it was actually primarily for missile defense applications originally. What we did is we took it into STK and made it generically capable of doing radiometric processing. So from 0.28 to 28 microns. That's the hairy edge of UV blue all the way to the long-wave thermal infrared. It's an STK plugin, so you've got all of the good stuff in STK, but now you can add sensors to that as well. And it comes with a lot out of the box. So you get an entire global model. It's a material map of the entire Earth. You've got a diurnal thermal model to heat things up, cool things down. You've got a celestial background. You have a library of custom 3D models, and you also have the ability to not just do these sensor visualizations, but you've got all those radiometric debugger outputs as well. So you can do analytics. So I'm going to show you really quick, before we get started, if you've never seen STK before, here's what I like to think of it as. So it's a playground. Here over on this side, you have all of the objects that are in your scenario. So I have an aircraft, a missile, a place with a sensor attached, and a satellite. Here we have our 3D model of what that looks like, and on the right-hand side, you have a 2D map of that. And the great thing is you can just play out scenarios. So you can say, I'll go to the beginning, I'll just hit play and slow things down. So I have my missile, and it's flying along this red line here, and the sensor on the place is tracking it. As that's moving past the frame, I have a satellite in purple, and that's starting to orbit by, and as soon as the missile goes out of frame, the sensor is going to start tracking that satellite. And thirdly, I have an aircraft that's going from north to south on a route, and when the sensor on the place is done tracking the satellite, it'll start tracking the aircraft. So the idea is, with STK, you could have all of these time dynamic effects, and with EOIR, it lets you do that radiometric analysis. So I can see not just what a sensor would be outputting, but what the electromagnetic readings, the debugger data would be in between those points. And why? So now you sort of know, okay, well, I can put all these different objects in my scene, and I can have these sensor properties. What do I need a target signature for? And specifically, a lot of times you know what your object of interest looks like if you have a target signature. A target signature is a description of exactly what some real object looks like. And it could be a real life measurement, it could be a completely synthetic but community standard tool, or it could be some hybrid of the two of those. And you know what your object of interest looks like, but you want to add the atmospheric properties. You want to add the radiometric backgrounds that are accurate for different times of day, times of season, or geometries. So now, with EOIR, you can do that. And some of the examples are, if you had a measurement of a rocket launch. That's actually what we're going to look at now for our first example. And maybe you've got all these different rocket launches in a database, and you wanted to see what they look like under different conditions from different sensors. Or you could say, you know what? I have a tool that spits out these rocket signatures under a set of parameters, and I want to look at the parametric detection capabilities for monitoring these with a set of sensors that I have. Or you could say, you know what? I don't know what my sensor properties need to be to detect these, but my customer says, you know, I have a target signature, you need to be able to detect it or characterize it or track it. How good a sensor do you need? And you can start playing those what-if games. So I'll briefly show you. So if I'm looking at a missile, and this is just an example object, you can see that in EOIR, there's a bunch of radiometric properties that you can set for this. So the EOIR shape properties that I'll be clicking on right here, it lets you build up a component-wise stack. So you can say, well, you know, I've got a set of, you know, objects, and maybe I can build the nose cone, the coupler, the cylinder. I can give these shapes. I can say it's a sphere, or it's a cone, or, you know what, I have my own custom 3D model. I can set the time as time dynamic, temperatures, or I can say it's a static temperature, or you can say, forget all this, I don't care about any of it, I have a target signature in a database that I want to use. And that's what these new target signatures allow you to do. It's allowing you to say, I don't know where every nut and bolt is and what the temperature of every surface is, but I have that data from a field measurement from a database or from a tool. So you can say, all right, well, we've got this, you know, this rocket launching, right? And I can take that modeled, measured, or combination and say, let's create a coordinate system off of this. I'll say along the nose is my reference angle, and I'll call that rho. And 90 degrees off of it is the side, and 180 degrees off a rho is the tail. You're looking down the back. And I can say, from that rocket launch, if I look down the nose cone, that's got the smallest intensity, because I'm mostly seeing just, you know, standard nose cones. But when I look at it from the side, I've got the largest intensity. I'm seeing the entire cross profile of the plume. And from behind, I'm seeing the tail, so it's a smaller cross section of that plume, but it's still a whole lot brighter than the nose. And I can say, all right, I can take all those dynamics, you know, those are the spatial dynamics, and I can say, not just do I have those variables, but I also have that varying over time as well. So maybe when I first launch, you've got a nice big plume, but then it shrinks, or it disappears completely, or it changes characteristics. You can also change the characteristics spectrally and say, maybe when I'm done burning fuel type A, I switch to fuel type B. Or I've got a certain change in fuel type profile that happens throughout the burn of this missile or this rocket. So from all that, you can say, all right, now that I've got this characteristic look of what this, you know, this missile looks like, or this rocket looks like as it's launching, how does that actually, you know, play out over time? And that's where Tull actually built up a scenario of this, and we can say, all right, well, you know, let's take a look at what that looks like. So this is a, you know, recording, but we'll actually have this video available that you can take a look at yourself, as well as the scenario itself. So if you were ever curious about what it would look like. And here, Tull has the, you know, introduction where we have this rocket, it's coming off a launcher. On the 2D window over here, we can see we've got different ground sites, and some of them have sensors attached to them. For example, this is going to be taking a recording of this, and as we play this out a little bit, we can see this is the burn profile over time. So that's that row of 0, row of 90, and row of 180, and each of these profiles with time. And we can see that, all right, well, this is actually going to get a little bit brighter, and then it's going to get a whole lot dimmer, and then it's going to drift off to practically nothing over time. And we can take all that data and say, well, what does that look like graphically? And one of the things I really liked in this analysis is what we did is you can start recording with your EOIR sensor at various stages of this launch. So you can see at time this, at time that, and you'll actually see this target signature diminish as you would in reality. So all of a sudden, we have all of our atmospheric properties, we have all of the radiometric background, but the target signature is exactly as you want it to specify it. It's got all the characteristics of the targets that you know best, and it's just putting it into context for the rest of the analysis. Then if we go back to here, so now that I can define how I'd like an object to look, I can now put it into any context for analysis that I would like to see later on. So you've got all those time dynamic properties driven by STK. So you've got your platform moving the way you'd like it to move, and you've got your sensors oriented on the platforms of interest, and you can have sensors on aircraft doing barrel rolls, or you can have sensors on satellites that are slewing or jittering, and you can have all those good time dynamic spatial properties, but now you've got the radiometric layer with EOIR as well. So you can add that sensor modeling capability. And one of the things I like to show, for example, I have an STK scenario where we have, so that rho and theta angle, you can actually see as I play this scenario out, as this is flying, you can see how these angles change. And this is a plot of that, and you can see every once in a while when this banks and makes a change, you see a fairly drastic change in your rho and theta angles. That's your relative geometry. And if you have a detailed target signature and knowing exactly what the signal is going to be at precise times when it's going to be crucial to detect or track this object, you now get all that fidelity here to do that analysis. That's target signatures, and what you'd want to do with them. But I also want to spend a minute to say, normally when you see STK, if you've seen a lot of it, you'll see examples like this where it's real complicated. You've got a million different objects, you've got a million different communications links and budget links and things that are adding complexity. But really, we know your life cycle starts fairly simple, and maybe you're starting at a white paper or a proposal, and you do a lot of analysis to win that proposal, to write that white paper, to do that research and development, but then that's going to feed into a contract, and then you're going to start writing high-level system requirements, and then you're going to be divvying those off to subcontractors or partners, and they're going to be given specs to meet, and maybe they meet them or maybe they don't when they do integration testing, and you need to assess what the system performance is as a result of that. Well, the idea is if you're using EOIR to do some of this early analysis, you can use the exact same analysis results that you generate for your white paper or your proposal later on during the middle or late phases of your life cycle. So for example, if you use the target signature validation in generating the latest and greatest detection algorithm in your research and development, and you win a proposal off of that, all the analysis that you've done now carries over so you can use that same input data and that same analysis techniques that you've already developed, that you've already got your post-processing for, to then say, all right, now we know how to write the requirements faster. We can actually get to work sooner. We can do the component testing and integration better with higher certainty. We can take all that stuff that we did and maybe a target property changes. Well, you've already got the framework to then regenerate that quickly, and there's no lead up time to get that started. And similarly, once you're operational, well, now all of a sudden you can do all the collection planning with the stuff that you use for your initial IRAD or your initial proposal, and do that to maybe design a new experimental collection that you want to try towards the end of life of your system. Or something goes unexpected and you've got a new target that you didn't expect and you're seeing an anomaly and you wanted to see, wait a second, how can we plug in a new target to characterize that? And you can do all of that again with the same set of tools, with the same set of analysis that you've built up already. But if you can define how an object is illuminating in all these different directions, that immediately allows you to say, well, why couldn't I do lasers the same way? And you can. So what we did is we said, well, let's design a few, generic capabilities that you might want to try and use this for. So we've been doing a lot of SSA work lately, and I said, well, one of the questions we had was if we had debris in LEO orbit, normally detecting that with an optical sensor is not a very good, option. One of the problems is if you have optical sensors, you can't see during the daylight, so when you might have the best solar angles on your debris, your sensor is also in daylight and you've got a sky background and you can't detect it. Or maybe you've got a little bit of detection capability when something's right at the edge of coming from sunlight to shadow, you've got a longer range. But what if you could illuminate yourself with a laser? And that's actually another scenario that Tall built up, saying, what if we were illuminating these objects in LEO and determining if they're detectable or not? You can also say, you know what, maybe we're doing laser comm analysis and we wanted to see what a radiometric transmission, power budget would look like. Or you could say, you know what, we've got a laser that we're doing one of these missions for, but we're trying to design a different pointing strategy. Maybe it's going to cut down on the latency between targeting objects. Or maybe I'm doing a different concept and I wanted to try a wider beam or a shorter beam or multiple beams. So once again, you've got all these different lasers that are possible, but how can you boil that down to the generic properties of these target signatures? And the great thing is, the two inputs that you need are what the beam pattern is, that's spatially, how is this beam shining, and also what does its spectra look like. And with these target signatures, maybe you have a radially symmetric beam pattern like these, and you can say, yep, these are good enough. Or you can say, I actually have an asymmetric beam pattern like this, and whatever optics you're using to focus, that laser are going to give it some pattern. You can design the spatial pattern, and you can also design the spectrum as well. And maybe the spectrum starts out simple as some nominal Gaussian, or maybe your optical surfaces involved have some type of transmission loss or characteristic that you'd like to capture as well. So the idea is these files are generic enough so you can do all of that and design exactly how you'd like your laser to look. So the scenario that we have, again, this one, I like this scenario a lot that Tall built because it has 3 different lasers, all of the same characteristics, so same beam patterns, same spectral patterns, but they're different pointing strategies. So just to give you a little bit of context, these are on the ground, co-located with a ground station, and they're shining at this LEO object as it's flying by. And we can see, all right, well, as those are shining on the object, what we're going to see is, we're going to see different readings. So our ground sensor is going to see different levels of irradiance from each of those beam patterns. And maybe the nominal beam pattern pointed perfectly gives us enough signal to detect, but the slightly offset, we're going to have some amount of pointing error, or maybe it's a rate error. Well, how is that going to impact our detection capability? You can do all of that analysis now with EOIR. And one of the things I like is you can now show some of that in context too and say, all right, well, now we've got all 3 of these laser beams, pointing up with different scanning patterns. What characteristics are detectable or are not detectable by this ground station that's similarly looking at this LEO. Again, all this analysis, can be carried on from the earliest phases to the latest phases of your life cycle. So, maybe this is a spin-off R&D project that you're doing now, but the good thing is you're not writing quick tools to do some analysis on the back of an envelope. You've got something that you can use throughout the entire life cycle of your project. So you're not wasting any of your valuable time on building something that might not be able to scale up later on, or might be flexible enough later on to do some more sophisticated or ad hoc analysis. And the last thing I wanted to talk about was, well, now that we can have all these neat illumination sources that are shining in different directions, we can switch the perspective and say, I'm not necessarily a sensor, looking at these objects anymore. What about the objects themselves? Now that they're dealing with a complex electromagnetic radiation environment, they've got a lot of light potentially that they're dealing with that they might not have been spec'd for. So when might this be important? Well, if you have an unintended illumination source that's messing up your sensor's performance, or you're worried about safety considerations. We actually had some folks that work on a field that do laser testing, and some of the other folks on base were saying, we don't know what operations we can perform because our guys are worried about getting cut in half by a laser that might get glinted off of an object that you're targeting. Or you might say, you know what, I've got a system that's spec'd to perform under certain conditions, but now I've got this crazy environmental illumination environment that I need to deal with. I don't know if I can do that or not. Well, this analysis would let you generate sample data or sample metrics or sample imagery that you could evaluate and test out. So what I like to imagine is, well, you can go to that same scenario that we did before, but instead of shining each of these lasers one at a time and doing the detection analysis, what if you turned on all three and you said, what if I've got somebody pointed directly at me that's pointed slightly offset and that's scanning in some pattern around me? And then you can reverse that perspective, and from the satellite or the debris in LEO's perspective, you can say, all right, well, how much incident radiation is hitting this object? What does it look like from this perspective? Maybe I've got a star tracker and I know, hey, there's enough stray light. This star tracker is going to start to get wonky and it's not going to work the way it's supposed to. I need to tone it down, or I need to change the orientation to perform adequately. So the idea is, with all these inputs, you can start to create your own what-if scenarios, and you can model how your systems will perform in a more complicated electromagnetic environment. So again, this is all building off each other. So hopefully, we want to see you guys win proposals. We want to see you guys write great research and development, and I am confident that this tool is going to let you do that and then carry it on later in your program and show, hey, the same tool that we used in step one to win this proposal, we can use during the integration. And hey, when it's time to finally do a victory lap, when we finally initialize and we're operational, I've got a little bit of ops time that I can squeeze out. I want to do my own experiments, and I want to prove that, hey, the very first R&D that I designed is still accurate, operationally. So, that's it. This is what I like to, the way I like to think about this is, I spent a lot of time going to the target properties, and I remember I think it was 11.5, I had all these folks that were saying, I want to be able to load in my own custom 3D model, and I want to be able to break it into solar panels over here and an antenna over here, and I want to be able to set the thermal properties of what these different components look like, and I'd like to set the BRDF of this to slightly different because it's maybe accumulate enough oxidation over time to change it. So all of these fancy multiple material properties, we can have geometric groups. A lot of folks can say, well, these are low-level details. I can throw all that out and say, you know what? I don't care. Just give me a custom point source signature, and I will define exactly what that looks like. And they're as simple as saying, you know what? We have a constant intensity of this value, or we can have a time-varying intensity profile, or we can have a radially symmetric beam pattern for a laser, and it's wavelength dependent. So you can do all of those things to say, if you don't have those real low-level target characteristics, but you've got a massent customer that knows exactly what their target of interest looks like, you can now inject that into the full context of STK and do your radiometric analysis. That's about it. So a lot of the details for this, the scenarios that Tal built, are going to go on to agi.com/EOIR. That's the EOIR portal where I like to put a lot of the resources that I have. So if you get a chance, we've got technical overviews. We have domain-specific example videos. We have long recorded 30-minute, 60-minute how-to videos that are done by our system engineers. And we also have technical documents as well as some short capability videos. So that's a good place to follow up. If you have any additional questions too, you can always, we've got our contact information here on the right. And Craig, do you want to?
Perfect, thank you. We do have some questions, Pat, if you have a moment.
Yeah.
Our first question is, does EOIR, where did my chat panel go?
Yes, EOIR.
Can EOIR model jitter?
That's a good question. So I have my screen up. So at the bottom, these are the sensor properties for EOIR specific sensors. And at the bottom, you can define the bands that are a part of your sensor. Then for each of the bands, you can define the spatial, spectral, optical, and radiometric properties. And then for the sensor itself, you can define things like smear and jitter. So you can turn motion blur on. So for example, if you're if you have two objects, one you're tracking and one is moving at a different rate, you can see that streak with the motion blur. You can also turn jitter on as well, and you have a number of different ways to specify how you'd like to characterize the jitter. So, for example, if you just say, you know what, I don't know what the jitter profile is going to look like, I'm going to use a line of sight Gaussian. You can just turn on some amount of Gaussian jitter, or you can say I have a specific MTF or PSF realization. Maybe I've got awesome vibration guys, and they've got me exactly what a particular jitter realization is going to look like. You can load that specifically up. Or if you just have a power spectrum, maybe your vibration guys characterize it via power spectrum, you can load that in as well. You can also add in explicit smear rates. So for example, if you have TDI and you have a quarter pixel smear, you can actively include that. Or you have some amount of D-weighted rate error, and it's not quite characterized well, but you know about what the D-weighted rate error is, you can add that in as smear. Similarly, if you have motion blur turned on and your object is, if you want to bounce something around with an aircraft, you can do that as well, and it will capture the gross motion blur from the beginning to end of that integration time period as well.
Can I have my target signature vary dynamically in time?
Yes, absolutely. So I like simple things, so I made sure that when I specified the format of these, you can specify different intensity levels at different times. So for example, this is at T, 0, 100, 200, and 300 in epic seconds for your STK scenario. And you can have the intensity go up, go down, and you can vary it spectrally as well. So for example, let me see if I have a spectrally varying point spread function. So here, the same way I could put time elements around the intensity profile, I can also put angular, time, any of those, and you can define it for different spectra. So you can say at 0.6942, 0.6943, 0.6944. So this is a little triangle that's just a nanometer up and down. You can say I have a little triangle function, and you can do that over time and angle as well. So it's a very generic input format, specifically so that tools like OptiSig and EMSig can translate directly over. When I was working with some of the folks that were using those tools, they were showing me the tables of output, and I said, oh, this is a piece of cake to work with. You've got all the right data. It's just chunked up, in an easy way to then convert over to this format, so I can have things very temporally, spatially, spectrally.
Okay, next question is, how fine is the emissivity model for the Earth's surface? I'm an English person, so I recognize that's English, but I don't really know the word there.
So the idea is how spectrally fine can you model things? And typically in the shorter waves, I go to about a nanometer. So our atmospheric model is characterized to the nanometer level, and you can actually specify it yourself too. So here's the spectral properties of my sensor, and you can say here's my band pass. This is just a visible band pass, panchromatic 0.4 to 0.7, and it's only broken up into 6 intervals. But I could change this to 1,000 or 100, whatever spectral fidelity I'd like to model in my sensor, and then it'll go to that level, based on the input source data. And I'd say the input source data is about at the nanometer level. That's one of the reasons why I specified the laser spectral profile to the nanometer level.
Okay, do we have one more question here? Okay, can I model the relationship between emitted and reflected light, for example, in the SWIR? And this person gives an example. Can this sensor detect this hot object during the day, even against the solar reflection?
Yep, absolutely. So you can model your objects. Now, depending on how you like to characterize your target signature, for example, if your target signature is specified in the SWIR, then you'll have all that fidelity throughout the entire 0.28 to 28 micron bandpass. And you could say, all right, well, what does this object look like against this Earth background? And the diurnal thermal model will raise the temperature up and down both with time of day and season. So it's northern latitudes now. It's the beginning of summer as far as I'm concerned. It's starting to get warm here in Pennsylvania. You'll see that hotter temperature throughout the day heat up and cool down. So if you had a constant SWIR or even a variable SWIR signature, you would see that signature composite with the background as appropriate. If you wanted to see reflections, for example, if you were looking at SWIR reflections, you would still need to specify what you're reflecting off of properties. So if I was shining a SWIR laser at a surface, you would still need to specify what the surface properties are, but you could say it's just a gray body, it's a constant reflectance, and you would then get the SWIR reflection off of that, again, with all the complexity of the background. And if you wanted that test panel, calibration panel to heat up and cool down. You can set a thermal profile for that as well. So for example, if I look at an aircraft and look at the EOIR properties of that, that's where I said, you could go to all those low-level details and you could specify exactly what, you wanted that object to look like. You don't need to go to that nth level of detail too. You could say, you know what, I'm just going to use a plate, let's call it a cal, surface. I'm going to set the surface temperature down here, and this could be static or time dynamic, and I can set it to gray body reflectance, a pre-built material, or you can even load in your own custom spectral response functions for the reflectance emissivity of your objects as well.
Cool, okay, great. Well, we have one more question here. Can we put in structured background clutter on top of base maps that STK provides, which I believe is about 1 kilometer GSD?
So you can include your own reflectance, emissivity, and temperature maps. So if you wanted to throw out all that information that's on the default Earth model and say, you know what, I have fantastic 2 centimeter reflectance, emissivity, temperature data, you can load that in as well. And actually on our portal page, there's a nice little walkthrough of how to do that. So right here is the using texture maps in STK, and this goes through a quick example of adding a surface reflectance map. I think I wanted something that was visible from space, so I looked at the pyramids in Giza and I said, let's load a reflectance map for those pyramids, and that's exactly what it looks like. We also, for the thermal analysis that we did last year, we used hotspots on the ground for wildfire detection. So we loaded our own custom-built temperature maps. They were actually based off of the EOIR temperature maps, but then we modified them a little bit. And we also had higher resolution source data that we included in some areas.
Okay, thanks, Patrick. I think that's it for right now. If we do have some more questions coming in, we'll answer those offline. Can we put the slide deck back up so we can remind everyone what the next steps are? So we do have training on our website at agi.com/training. You can always sign up for those. We've got some virtual trainings coming up, so you don't even have to leave the comfort of your own office. If you want to join us, you can. Also, you can always talk to an engineer at info@agi.com. And then you can always stay tuned to agi.com/blogs for upcoming webinars. And then this video that we recorded today will be available on our YouTube channel at youtube.com/analyticalgraphics. And make sure that you subscribe to that. And we're posting a whole bunch of great data up there and some great tech talks. So please go there and check that out. And again, thank you for joining us. And I hope to see you at our next webinar.
All right, thanks.